morning. We begin lecture 40. To avoid confusion, they have asked us to keep the numbering sequential. So lecture 39 was actually a review lecture, which will be made up with another content lecture. But for now, lecture 38 and then lecture 40, the continuation is from lecture 38. And since it has been almost a week since the last lecture, we'll go through a little bit extended review because we need to cover, build on what we have already covered. Today we will probably cover the two most interesting concepts in channel capacity, which is water filling, and then two variants of that, water filling over time, water filling over frequency. Once you understand this, the entire concept of capacity, how do you achieve capacity, and all of those answers start to fall into place. So hopefully this will be an interesting lecture. A very quick run through. We are having as the foundation Shannon's definition of the capacity of AWGN channel, B times logarithm base 2 1 plus gamma. Gamma is the SNR, and the units are bits per second. So this is a capacity that scales logarithmically with respect to SNR, linearly with respect to bandwidth. And that's the reason why very often we look at a normalized capacity, which is C over B, per unit bandwidth, which is bits per second per hertz. Okay. A classic example where we saw a channel with bandwidth 30 kilohertz, three different SNRs caused by the three different fading coefficients. Each of them has got a certain probability. Okay. Now, how would you describe this channel? Is it a very bad channel, or is it a okay channel? Is it a reasonably good channel, a mild channel? What would your description be? The bad state occurs fairly infrequently, so it's a reasonably okay channel. So keeping in mind that capacity is not about channels with good SNR, because that you know how to get the benefit of that. The challenge is how do you get the maximum out of channels which are not so good in terms of SNR. That's what we're going to be addressing today. But the example that we looked at had three states, three different probabilities, and that gave us a computation of two important quantities. One is if I calculated the average SNR based on the probabilities of the different SNRs, and then calculate a capacity, that would be the capacity of a AWGN channel with the same average SNR. That came out to be 223 kilobits, almost 224 kilobits per second. On the other hand, recognizing that actually the issue is that SNR directly affects the capacity, so we then look at an ergodic capacity where it's a capacity multiplied by the probability. When we did that calculation, it came out to be 199 kilobits per second, substantially less than the corresponding AWGN channel capacity, but nevertheless, even this 199 kilobits per second is going to be a challenge to achieve under different SNR conditions. Notice that this capacity is for this specific scenarios in terms of SNRs and the probabilities of the different SNRs. And using the Jensen inequality, we showed that the ergodic capacity will always be upper bounded by the corresponding AWGN capacity. Okay, so the summary is that we have a channel typically would have been indicated by an AWGN source. Now we also have a fading coefficient, so which means that this is our fading channel. For this fading channel, I need to come up with a suitable encoder decoder or a set of encoder decoders that will achieve capacity. So basically that's the underlying problem statement. Some observations that we have made already. Whenever SNR goes down, capacity is very adversely affected. As much as possible, we would like to use all the available channels. Maybe now that we have a little bit better knowledge, we would say available channels with optimum power allocation. Optimum power allocation, would you agree? Because it's not just about using all the channels, it's about using them with allocating the power. So the good channels would have, so with optimum power allocation. But power allocation requires you to have what? In order to do optimum power allocation? CSIT. So this requires CSIT. Okay, if you have CSIT, then you can use more channels and you can also use the optimum power allocation. And of course, the intuition is that give more power to the channels with the higher SNR and therefore get the maximum out of it. Now, if you did not have without CSIT, what's the best that we could do? What is the best that we could do? It would be, if you insist on no outage, then I'll be severely constrained. So the best that we can do is channels capacity with outage. Right? These are the scenarios where you say, okay, some percentage of the time data will not go through. So capacity with outage. So these are the concepts that we have covered, and this is what we will build upon. So the notions of CSIT and CSIR very important, and how they will impact our capacities are visible right at this top level. Okay. So now let's go a little bit deeper, just to sort of quickly run through. The three cases are when I know only the PDF, then when the channel receiver knows the channel state information, and the way we would achieve a capacity in this case is to have very long code words. Again, we talked about the delay and the complexity of such systems. Now, capacity with outage starts to bring into the realm of practical implementation. So if I have a system where the channel SNR is changing, I'm going to model it as an equivalent channel where the SNR remains constant for a block of data, and then between blocks of data the SNR can have an arbitrary change. So under this set of conditions, I now have to pick which SNR will be my threshold. Above that SNR, I must guarantee that the information is communicated reliably. Below that, I will consider outage. So if I consider gamma 1 as my threshold, anything below gamma 1, at gamma 1 or below is going to be an outage, then we showed that we could actually achieve a fairly high data rate without the transmitter knowing the information. All we are saying is under bad channel conditions, I'm going to consider it as an outage, so therefore this. So that is a good data point for us to keep in mind. Okay. So to summarize, outage will be if the SNR is below the threshold that we have set, and the capacity with outage will be the capacity at the SNR for which I have designed into 1 minus probability of outage, because there is a certain percentage of the time my SNR will be below gamma min, and that's an outage scenario. And so please do not forget this, because if you forget it, you will get a more optimistic result, because since the transmitter does not know, it will continue transmitting even when the channel is below gamma min, SNR is below gamma min, and that data will be lost. Okay. So maybe a point that we can make about so CSIT versus CSIR. CSIR versus CSIT. What are the penalties if I do not have CSIT? What if I basically in this scenario where I'm transmitting designed for some gamma min and I'm transmitting. So I believe the points that we can make in terms of the disadvantages are, first and foremost, there's loss of data, right? There is loss of data. Loss of data during outage, and we said, okay, I don't care about, I can't do anything about it, so I'm helpless. So there is a loss of data during the periods of outage. Probably another related element which we may sort of omit, but it's going to be important in the context of today's lecture, is that we have also wasted power. Is that a correct statement? Because this data did not go through. So there is a waste of power, okay, Tx power. Now if I had CSIT, then I could have avoided both of these things. One is I would not have transmitted, so there won't be any, there's no notion of loss of data. Second is I would have used this transmit power for better scenarios to transmit more data. So CSIT sort of avoids both these things and actually takes benefit from both of those. Okay. So the context of CSIT is as follows. We have the channel as before, a fading channel, fading coefficient plus AWGN. Have to design the encoder and decoder. The only difference now is that I can estimate SNR and I can feed it back. I can feed it back for two purposes. One is to choose the encoder decoder, but more than that, to also do power allocation, because now I can do differential allocation of power for the different channel realization. So this power allocation block is what we are going to focus on. That's where we had stopped at the end of last lecture, saying, okay, yes, in principle, if you give me an SNR, I know how to design the encoder and decoder. But how do I allocate power? What is the optimum power allocation? What's the intuition behind the optimum power allocation? And then how does it have ramifications in terms of our understanding of wireless capacity as a whole? Okay. So yeah, we have several options for when the channel is poor. Our assumption is going to be that under certain conditions, you will not transmit power, you will not transmit at all. And when the channel conditions are according to channel conditions, if it's above the threshold, then you will adapt both the power and the transmission rate. So basically the coding, decoding as well as the power allocation will be adapted. The assumption is that the channel information at the transmitter is perfect. That means no errors in estimation and is instantaneous. See, because these two things are ideal assumptions, because typically you are estimating it. So estimations can have estimation errors associated with it, and then there is a finite delay in feeding back. So in that, if it's a very fast changing channel, then by the time the feedback reaches the transmitter, something could have changed. Right? So we are assuming that under ideal situation, that the knowledge at the transmitter is perfect and is instantaneous. Okay? So that's another important element. So now comes the power optimization part, and the power constraint is that I have to allocate power for each of the SNR scenarios. So basically that is P of gamma is the power that I am going to allocate for a particular SNR, and I have to ensure that I don't do arbitrary allocation. So there is a constraint. So the average power must be maintained across all SNRs. So the power allocated for different SNRs times F gamma of gamma D gamma is must be bounded by P bar, or if I divide by P bar, I get a normalized constraint. So with this, we wrote down the capacity requirement. So we are looking at the capacity, or to compute the capacity of a time varying channel. We want information is available at the transmitter, and I want to do optimum power allocation subject to a average power constraint that is given by this expression. So the statement of power of the problem that we now have is, I want to maximize capacity. I want to maximize it under optimum power allocation. So the power allocation, if you denote it as what we have indicated by red as a normalized coefficient, it either boosts gamma or decreases gamma. That's the decision that you have to make. Now you're going to maximize this capacity over all possible power allocation schemes. Okay? So it's maximization of capacity. No, hopefully there's no confusion about what you're maximizing. So you're maximizing capacity under all possible options for P gamma, and P gamma must satisfy the average power constraint, which is given by this this expression. Okay? So the way to visualize, once you have obtained the optimum power allocation, what will I do? What will we do? We will design the different encoders. We will take the channel conditions. We will quantize them into different SNRs. For each of the encoder decoder pair, the minute I know that the current channel conditions has got gamma j, then I pick the corresponding branch, put the apply the power allocation, and then feed the information into the channel. And assuming that the channel is constant for a period of time, this packet of data will go through and I will achieve the best possible performance for all SNR conditions. So it's a combination of the concept plus a practical realization, but the assumption is that somebody has told me what is the optimum power allocation. So today's class is all about how do we find out the optimum power allocation and how to leverage that. So let us focus on that. Typically our optimization problems, you have an objective function, and the Lagrangian technique also incorporates into the objective function the constraints on the variables of optimization. So one thing that we are going to do, which you may not be familiar with, is to treat, see, basically P of gamma is a function. right? For each gamma, you have to specify p. So I'm going to treat p of gamma as if it were a single variable. Okay? So again, it is a permissible method, and it actually gives us a very good insight into the method, into the technique that we are trying to. So the objective function is for us to maximize capacity. So this is the capacity part. I want to maximize the capacity. This is the power constraint, average power constraint. Okay, it's a constrained optimization. Okay, so basically I will differentiate with respect to the variable p of gamma and also with respect to lambda. When I differentiate with respect to lambda, I will get the average power constraint. So that is already one equation that is available to me. Now the key thing is I want to differentiate with respect to p gamma. Okay, so the partial derivative of the objective function is a function of p of gamma and lambda. I would like to differentiate this with respect to p gamma. As I said, I am treating that as a variable. So we had talked about the differentiation of an integral. Fortunately, neither the upper limit nor the lower limit has the variable with which you are differentiating. So only one term, which is the derivative of the integrand, comes into play. So it's easy for us to write down this differentiation. So basically, it will be integral 0 to infinity b times, I cannot logarithm base 2, I want to write it as we indicated before, logarithm base 2, we write it as logarithm base 10, log base e of the quantity divided by log base e of 2. So rewriting this becomes b by ln 2. I write the numerator as in terms of as a natural logarithm, which allows me to differentiate. When I differentiate, I get the argument in the denominator, 1 plus p of gamma divided by p bar gamma. Then I have to differentiate with respect to p of gamma. So that gives me gamma by p bar in the numerator. F gamma of gamma, does not affect the and then we have minus lambda times, maybe just to avoid confusion, let me just write it as two separate quantities. This as d gamma, again lambda times integral 0 to infinity f gamma. I'm going to rewrite this as a, does that make a difference? It should not, but I'm just going to rewrite this as 0 to infinity p of gamma, f gamma of gamma, d gamma minus p bar. Okay, so basically, so when I differentiate with respect to p gamma, I get f gamma of d gamma. So this is the value that I get after differentiation. Please make sure that, and I would set this equal to 0. Notice that we are dealing with the probabilities and we are dealing with power allocation. So all the quantities inside are positive. So if the integral has to go to 0, the integrand must be 0. So basically we will set the integrand to be equal to 0. And under that condition, what we will get is b divided by ln 2, 1 divided by 1 plus p of gamma by p bar gamma. This is equal to lambda times p bar divided by gamma. Okay, please check that I have not made a mistake. Rewriting this, what we will find is that 1, I will just write it in a different color, 1 plus p of gamma by p bar of gamma. I have also done the inversion. This comes out to be b by ln 2 gamma divided by lambda times p bar. Okay, one step away from the answer. P of gamma divided by P bar, which should give me the optimum solution, can be written as 1 by gamma naught by 1 minus gamma, where 1 by gamma naught is a constant which is given by B divided by lambda P bar ln 2, 1 by P bar, 1 by B by lambda P bar ln 2. Okay? Why do I say that this is a constant? What are all the things that are constants? Let me tick. The bandwidth is a constant, ln 2 is a constant, average power is a constant, the Lagrangian multiplier is a constant. Okay? So, all of these are constants, so I can treat 1 by gamma naught as a constant itself. And you may wonder, why did you call it 1 by gamma naught and not as gamma naught? The answer will come in a moment with the, so I just want to make sure that we are comfortable with this expression. So, what have we done? We wrote down the capacity with the constraint, differentiated with respect to the function, treating that as a single variable, and showed that the optimum solution should satisfy this condition, and the condition is that P by gamma by P bar, P of gamma by P bar is 1 by gamma naught minus 1 by gamma. Okay. Now, very important, the interpretations. So, first and foremost, this has a notation that I would like to introduce now. When we say x of plus, this notation basically says you take the maximum of x or 0. If x is a positive quantity, you take its value. If it becomes negative, basically it's bounded by 0 on the lower limit. Okay. So, P of gamma by P bar can be written as 1 by gamma naught by minus 1 by gamma with a plus, because power allocation cannot be negative. You cannot say I'll allocate negative power. So, I can either allocate 0 or some positive value of power. Okay. So, this is the condition, and this is true if gamma is greater than or equal to gamma naught, because only under that condition the argument will be anything other than that, it will be 0 for gamma less than gamma naught. Okay. So, what I want you to do is just take a moment to just sort of look at the expression that we have obtained. Is it intuitive? Does it agree with what we at least have understood about capacity so far? It says that the power allocation that I am going to do is going to be 0 for certain channels below some gamma naught, okay, which is very intuitive, because if the channel gets very bad, I do not want to allocate any power. Okay. And as I get to better and better channels, I am going to allocate more and more power. Again, very, very intuitive. So, but the most interesting thing is the interpretation when we actually draw this graph. And many times this is the graph that sort of enables us to sort of say, oh, okay, now the whole thing sort of makes sense. So, if you draw SNR on the x-axis, and very interestingly 1 by SNR on the y-axis, you say, okay, there is no information in this graph, but actually it does have. Basically, it's 1 over gamma. So, it's a graph of 1 over gamma. Okay, that's what we are plotting. Now, I want to interpret this result. It says that there is some SNR gamma naught, which corresponds to 1 by gamma naught as a, once you know gamma naught, 1 by gamma naught is a value that is present. It's a constant. Okay. The interpretation of the optimum power allocation says that in this region below gamma naught there is no transmission, and above this portion there is transmission. Okay, this is where transmission occurs. Where are the very good channels? They are extreme to the right here. These are the very good channels. I am using a qualitative statement, but basically, and how much power do they get? 1 over gamma naught minus 1 over gamma. Notice they get the maximum power allocation. So this is in some sense 1 over gamma naught by minus 1 over gamma. This is the power allocation for this particular value. So you can take any SNR. As you go to higher and higher SNRs, you are getting better and increasing levels of power allocation. Okay. No transmission basically means 0 power allocation in this region. 0 power allocation. So when the channel is very bad, I don't allocate any power, I don't transmit at all. I take the power that is available and then do a basically it's a progressive power allocation. Okay. Now very often if you want to visualize this looks like a bowl or a basin where you are filling water, and this power allocation is interpreted in terms of water filling, because inside the bowl when you fill water, the depth of water tells you how much power you are going to allocate for that SNR. Okay. So this is where the name water filling comes from. Basically think of the blue line, you have to visualize it as a, complete the bowl, okay, and then water filling. Okay. But so this is where the famous term water filling comes from. Okay, you are looking at an inverted bowl and then the SNR is being filled. Okay, so let us quickly consolidate whatever we have understood so far in this discussion. So the summary is that power is allocated only if the SNR is greater than or equal to gamma naught. SNR is greater than the threshold. Below the threshold, we don't allocate power. Okay, so this is like a threshold. Gamma naught is like a threshold value. Now the key thing is, yes, it's very nice, the interpretation is good, intuition is fine. What is gamma naught? We need to calculate gamma naught. So that's what we are going to be doing. So under this assumption, what is your capacity? Under optimum power allocation, so basically under water filling as the assumption, it is not 0 to infinity, it is now gamma naught to infinity, b times log base 2 of 1 plus the power allocation times gamma. So the power allocation is done by the following algorithm: 1 minus gamma naught by 1 minus gamma. That is the power allocation component. This multiplied by gamma, that would be my SNR, multiplied by f gamma of gamma d gamma. Okay, that is the equation for the capacity. Okay, of course, you can easily simplify. Just take the expression. You can write this as gamma naught to infinity b times logarithm base 2 gamma by gamma naught f gamma of gamma d gamma. Okay. So it's a difference of powers. When I do logarithm, it becomes basically it becomes the ratio of the two values, one, and that's what I have got here as the term, and that will directly impact my capacity. Okay. So as gamma increases, the capacity will increase. Okay. So my basically I have come up with the optimum power allocation, which introduces a variable gamma naught, and now how will I estimate gamma naught? That is the last step. Gamma naught comes from the other constraint on the average power constraint. So integral gamma naught to infinity p gamma by p bar f gamma of gamma d gamma equal to 1. So this can be rewritten as gamma naught to infinity 1 by gamma naught minus 1 by gamma f gamma of gamma d gamma equal to 1. Okay. So it's an integral, it should satisfy this condition, and usually this is the quantity that we are interested in. We obtain it through numerical integration. numerical integration, and it's an iterative process. You assume some gamma naught, you calculate, it comes out greater than 1, then you know, okay, I have to adjust. It becomes very small, then you kind of do iterative and then base. So numerical integration plus iteration, and again this is something that is not difficult at all to do, you can easily find out. Okay. So gamma naught evaluated numerically. So the final statement is that the optimum power allocation goes via water filling. It has to have a reference point, what is the water level, and that water level has to be obtained through a numerical calculation which takes into account the average power constraint that you have, but once you have that, it is something that is easily achievable. Okay, let's re-look at the example that we have been studying. It's the case of the not so bad channel, the channel with the 3 SNR states. So gamma 1 equal to 0.833, P of gamma 1 equal to 0.1, gamma 2 is 83.3, probability of gamma 2 is 0.5, and gamma 3 is 333.33. Probability of gamma 3 is 0.4. Now this is the channel condition that we have done. What we have already computed is what is the capacity with outage. Capacity with outage. Okay. What is the best that we could do in terms of capacity with outage? Assume 10% outage, and therefore you will get the capacity of whatever is the capacity corresponding to 83.3 multiplied by 1 minus probability of outage. So 1 minus probability of outage into capacity of gamma 2, right, and this gave us a number which was 172.75 kbps. Okay. Now the question is, will water filling beat it? The question is, and by how much? And as I mentioned, this is not a very bad channel. So getting capacity out of this is with outage was somewhat straightforward. But even under this average channel condition, let's see what sort of benefit we get from. So obviously, what we would like to say is, I would like to exclude gamma 1. I don't want to transmit at gamma 1. So my gamma naught, the threshold, I'm going to say is greater than gamma 1. Am I right? That's the threshold. I don't want to do any transmission at gamma 1. So I am going to set my threshold greater than gamma. So under this condition, I have to calculate gamma naught. Calculate gamma naught. This is a discrete state. It's not an integral. I will get a summation. So I equal to 2 to 3. That is gamma 2, gamma 3 are acceptable states. Under that, the power allocation condition is 1 minus gamma naught minus 1 minus gamma I into F gamma of gamma I should be equal to 1. Okay. So basically, I've written the average power constraint for these two SNRs. So this becomes 1 by gamma naught minus 1 by 83.33 into 0.5 plus 1 by gamma naught minus 1 by 333.33 into 0.4 equal to 1. That's the average power constraint. Basically, this is how much power allocation we are doing, and based on the probability. So based on this, please verify that gamma naught comes out to be 0.89. 0.89. Okay. So now the capacity with outage comes out to be, again, only the two SNR states that we are considering, gamma 2 and gamma 3. It will be B times logarithm base 2 gamma I by gamma naught. Remember, that's the capacity with water filling, F gamma of gamma I. Okay, so this will be 30,000. That's common. We'll take it outside. First one is logarithm base 2 of 83.33 divided by 0.89 times 0.5, that's the probability. Second one is logarithm base 2 of 333.33 divided by 0.89 times multiplied by 0.4. Please do complete this calculation. Verify that this answer comes out to be 200.82 kbps. So even under nominal channel conditions, water filling extracted almost 30 kilobits extra, the kbps extra. Okay, that's a significant percentage. So actually, water filling can, in many channel conditions, it can do much better. So, but we still agree that water filling has a benefit. Therefore, this is something that we would definitely like to keep and exploit to the maximum. Okay, any questions? So water filling is all about finding the water level, allocating power such that the better SNR channels get more power under the constraint that there is a satisfying overall power constraint, and this enables us to get the maximum out of in terms of the capacity from the channel. Okay. Always good to look at a few exceptional situations. Okay, first exception situation. So this is like case 2 of the same problem. What would have happened just for this thing, if you had taken gamma naught less than gamma 1, what would have happened? You are telling that you are going to use gamma 1 also into your equation, and you are going to do water filling. Nothing says that you can't do that. So basically, it's a perfectly legitimate because you're saying, okay, fine, gamma 1 is not so good channel, but I still want to do power allocation for that. So now this condition will be summation I equal to 1 to 3, 1 by gamma naught by 1 minus gamma I into f gamma of gamma I, this equal to 1. Okay. You solve this, of course you will get an answer. Gamma naught is equal to 0.89 comes out to be the answer. Okay. What is gamma 1? 0.83. So actually gamma naught is greater than gamma 1, and we say, okay, there is a problem, there is a contradiction. So under this condition of trying to include gamma 1 also, you find that actually there is no water level that will satisfy the condition. So which means that I cannot in principle do water filling for this case, because I cannot find a gamma naught. Okay. So it's very important that we choose gamma naught such that I get a valid gamma naught, and then because only getting a valid gamma naught is a prerequisite for me to do water filling. Because if I don't get a gamma naught, then basically I don't get a water level, then I can't do water filling. So in this case, I cannot do water filling, because I cannot estimate gamma naught which satisfies the condition that I am trying to achieve. Because if I try to do this under this, I will get negative power allocation, which is not permitted. So cannot do water filling in the conventional way. Okay. So keep in mind that it's all about finding the optimum gamma naught and finding the best way to do it. Okay. So we have now come to the last stage of saying, what is this thing about doing water filling over time? What is this thing about water filling over time? That's one of the key concepts, and the concept can be interpreted as follows. I have a channel, a time varying channel like a Rayleigh fading channel, and the SNR is going to fluctuate, right? Something, it keeps going up and down. And the way to visualize this channel is that there is probably a threshold below which I won't want to transmit. So when the signal is in a deep fade, I will not transmit. So there are zones of no transmission. So in this time period, so on this axis is time, this is gamma. Okay. And so time on this axis. So during this period, there is no transmission because it has gone below, and from our discussion on water filling, there is some threshold gamma naught below which we will not do Now what about the possibility above this point? So what we do is we can treat this as basically do a stairwise approximation of the SNR and treat each of these as the corresponding, let's call this gamma 1, gamma 2, gamma 3, those are the SNRs. Map these gammas to the corresponding encoder decoder pair. Where is that figure? Corresponding encoder decoder pair. So, gamma 1 means, okay, this encoder, this decoder. What is the power allocation? The power allocation is done via water filling. Okay. So, the power allocation is done via water filling. So, we know that the minute I have an SNR, I have an encoder decoder which I can work with. All I needed to know was the power allocation, and the power allocation will basically come as 1 by gamma naught minus 1 by gamma j will become my power allocation for that. And how did I get gamma naught? By computing the average power constraint. Okay. So, how can I get the maximum out of a fading channel? Is by discretizing my SNRs, and for each of these discretized values of SNR, I have an optimum encoder decoder pair. Water filling tells me, based on my average power allocation, I can tell me how much power I should allocate for the different SNRs. I use that information also and get the maximum in terms of the capacity. Okay. So, the solution that what we are talking about is for you quantize the SNR, quantize the SNR values, and for each SNR segment, choose the appropriate encoder, choose the encoder decoder pair, along with power allocation, along with the optimum power allocation via water filling, Okay. That is what will give me the capacity of a wireless channel. Well, can it beat the Gaussian channel with the average SNR? No, but this gets me pretty close to the but this does require me to have knowledge of the channel at the transmitter. CSIT is absolutely essential for me to get this one. Okay. Any questions? Last and the most important concept, water filling over frequency. Okay, now what is this? I'm going to pose you a particular framework, but for that, the framework that we have considered here, if I were to describe this, this is a narrow band system with frequency flat fading. Okay. Because what did I do? I said I have an SNR, and I said my entire channel is going to experience the same fading conditions. That is possible only if it's a narrowband system which is experiencing flat fading. Okay. But it is a system with time selective fading. Because the channel changes with time, the SNR changes with time, and I have achieved capacity for a narrowband system under time selective fading.
Is this done continuously over time or within chunks of time?
Well, you would have to design your system looking at all of time as a constraint, because the average power allocation has to be done over the entire duration. So you must have an idea of how the SNR is going to vary over the period that you are going to look at. Only then you can satisfy the average power constraint. But once you have done that, when you actually are implementing it, it will be more on, okay, currently it is gamma 4. I take the gamma 4, then it's gamma 5 or gamma 10. So basically, once I have designed the system, it is based on each segment. You can make a decision. You don't have to design it based on the data. Based on the statistics that are available to you, you design the system, and then you implement it in practice in this fashion. Okay, so this is a narrowband system with frequency flat fading. That means the whole band is experiencing the same fading, but it is time selective. Okay. Now I want to change the assumptions. So it's a wideband system. Wideband system, that means immediately it is frequency selective fading, correct? Frequency selective fading, but to make matters simple, we are going to say that it is time flat. That means it is not varying in time. Okay. Now how does such a channel look? I have the 3-dimensional axis. Frequency selective fading means there is multipath components, correct? And if I look at it across time, there is no change. The multipath components are remaining the same. So the first tap remains the same value, second tap remains the same value, third tap remains here. I look at it at beyond some point, again same framework I obtain. Okay. So this is a frequency selective fading channel, but it is time flat because nothing is changing as far as time is concerned. Okay. Now how would you model such a channel? It is like saying I am taking my data Tx, it is passing through a wideband channel with a frequency response h of f. Note, keep in mind the h of f is no longer flat because this is because there is a frequency selective fading. Now to this I add noise eta, okay, and then I have to design my receiver. Now the question is, how do I achieve capacity for such a channel? Okay. We then say, okay, let us look at what h of f looks like. H of f is a continuous waveform, okay. But I can discretize the frequency response of h of f into some chunks. Okay, I am going to use uniform. Each of them has got a band width b. So this is h of f. This is as a function of frequency. I basically have quantized the response. Okay. Now I want to ask you what is the SNR of this particular bandwidth B. Now this bandwidth B is a flat fading channel. So if the SNR of this particular channel, let us say gamma j, is actually the SNR that I would have had in the absence of fading multiplied by mod h of f whole squared, where f corresponds to basically this gain corresponds to the particular segment with the particular gain. Okay. So the gamma j is not a constant across all the channels. It is something that depends on the channel gain, and depending upon the frequency selectivity, I will get a channel gain. Okay. Simple statement. So what does this look like? This looks like large number of narrowband channels with bandwidth b, each of them with different SNRs. Okay. How do I get capacity out of it? Water filling. Water filling over time or frequency. So basically again decide that there may be some threshold below which you do not want to use any transmission. You do not want to use any transmission. So I do not want to transmit in this region. I do not want to transmit here, but I want to transmit in the other portion. I do not want to transmit here also, but I want to transmit in the rest of the spectrum. Now you go back to Proicus and say, I want to transmit over this band, but I don't want to transmit here, here, and here. Sorry, I don't have a modulation scheme that does that, because once you choose the bandwidth, what does your spectrum look like? Your bandwidth spectrum looks like this, right? Basically the signal spectrum that you have, you cannot say I don't want any spectrum, I don't want any information content here, here, and here. That's not possible. Okay. So this is what drove or led to OFDM, where we said, okay, don't transmit one wideband carrier, instead transmit narrowband carriers. Once you have narrowband carriers, I can achieve the capacity of the system. I can achieve by doing two things. One is I can do power allocation, I can do no transmission on some frequency bands, which I cannot do in a single carrier system. So it's only possible in a multi-carrier system, and this is what will achieve capacity. Okay? So final thing, how did Shannon want to achieve capacity of the telephone line channel? What is this? A telephone line channel is nothing but, let's assume it's not time varying, it's a wideband channel with frequency selective. So what should you do? Divide it up into narrow bands and do what? Water filling. Water filling. So what should you do for water filling? If this is the SNR plot, 1 by SNR will be this, 1 by SNR, this is the threshold, and this is 1 by SNR, this is SNR, and water filling is done like this. So you can do 64 QAM on the first carrier and then BPSK on the last carrier, and with appropriate power allocation. And this is what gets you many, many megabits per second on a telephone line when all you were using it for was 64 kilobits per second. Okay? So again, water filling, one of the most powerful concepts in capacity. We have water filling over time is what we were trying to solve, but it helps us address the broader issue of what do you do with wideband signals which have frequency selective fading. No problem, I do water filling across the different frequencies, choosing to do no transmission on some carriers. Now the most important thing that I want you to think about, I'll just mention it in passing in tomorrow's lecture, what happens if you have a wideband time varying, doubly selective channel? What do? You will do water filling over frequency and time. That's it. That's how you get capacity of a fading channel, wireless channel for a broadband system. Okay, thank you. We'll see you tomorrow.